All right, so we talk about the theoretical idea behind hash functions. We also already seen the constructions, Merkle-Damgard and sponge constructions. Now it is time to see dedicated designs. As I already mentioned, the old designs use Merkle-Damgard constructions. So the algorithms that we are going to talk about now, MD4, MD5, RIPEMD, SHA1, and SHA2 are Merkle-Damgard constructions. So here we are actually talking about the F, the compression function in our Merkle-Damgard picture. So let's start with one of the oldest but well-known algorithm, MD4. It was developed by Ronald Rives in 1990. It has the block size 512 bits, message digest length, in other words, the output of the hash value is 128 bits. It consists of 48 rounds, and one round is depicted here. So you just repeat this process 48 times. And this type, its type is Merkle-Damgard. So ID is as follows. We have 4 words, A, B, C, D. Okay, these are 32-bit values. Here you fill it with IV. Then in the first round, you perform some F operation, which is just logical operations, which I will talk about them in MD5. So you just combine these 3 words, add it to the first word. This is modular addition simple. So addition modulo 2 to the 32. Then you start adding 32 bits of your message here in the first round. Then you add a constant, rotate this word. Then, it was the first word, but in the next word, it becomes the second word. This goes here, and this one goes here. So this is your single round. You do it for 48 times to just feed one single message block from 512 bits. Okay, so at the end, the values here will be used to produce the output. Okay, so it is as simple as that, but don't forget that if you go back to Merkle-Damgard picture, this F function is actually 48 many rounds of this picture, okay? Recall that it took 2 inputs, IV and message block. Here, your IV will be here, 128 bits, and your message block is fed from here 32 bits by 32 bits each round. Okay. So is it secure? And the answer is no. If we talk about collision resistance, generating a collision takes a few microseconds. So it is very easy to produce MD4 collisions. There are some attacks that find pre-image which requires 2 to the 95 operations instead of 2 to the 128, if you recall the brute force attack. So this was a IETF standard hash function defined in RFC 1320, but retired in 2011 with this RFC. But this, as you can see, this is very late. I mean, people should have stopped using it at the beginning of 2000s. It influenced the later designs, MD5, SHA1, and RIPEMD. I will move on to MD5 and explain it in more detail because it is, some people still think that this is secure, and I also learned from computer teachers in Turkey that they thought that MD5 is secure, and they told me that they teach it in the class as if it is secure, but it is not. It's surprising that people still use MD5. So it is again developed by Ronald Rives in 1991 to replace MD4. The specifications are almost the same. Block size is the same. Message digest length is the same. But now the number of rounds are increased. Instead of 48, we perform this picture 64 times. Okay. And the difference between MD4 and MD5, aside from this number of rounds, you can see that there's an extra addition here to provide, more confusion. So in the MD4, this wasn't here, but in the MD5, we have extra addition here. So let's look at this F function. I told you that it takes 3 inputs and provide 1 output. So F function works like this. In the first 16 rounds, when you take the 3 inputs B, C, D, it performs B and C, or not B and D. In the following 16 rounds, it performs this. In the following 16 rounds, it simply performs XOR operation and so on. So as you can see, the F function here is really something really fast, because this is just 3 or 4 logical operations which you can do in a very fast way. This is why MD4 and MD5 are really fast. But since the design is really simple, it is also easier to break. For instance, collision resistance. So generating a collision requires 2 to the 18 operations, which takes less than a second on just a laptop. Preimage resistance is also not as expected as it should be. Instead of 2 to the 128, you can find preimages performing less than 2 to the 128 operations. So in 2004, it was shown how to create a pair of files that share the same MD5 checksum. In 2005, Lenstra, Wang, and Weger demonstrated construction of 2 X.509 certificates with different public keys and the same MD5 hash value. And in 2008, it is shown how to fake SSL certificate validity, so certificate authors should stop using MD5. So if you remember, I think it was around 2009 or 10, almost every browser stopped using MD5 certificates. So just after one day, you started to see red errors when you visited the web pages you visited regularly. It was due to this fact, because browsers stopped accepting SSL certificates that use MD5. But the thing is that in 2012, the authors of Flame malware used an MD5 collision to forge a Windows code signing certificate. So Flame was one of the famous malwares. I think it was one of the first to, spread international and affect a lot of computers. So its success actually depended on the MD5 collision, which people should have using years ago. So here's an example. This is an X1 and X2 are 2 different message blocks. So these are 512-bit message blocks. They are different, and only different parts are shown in red. So this is of course represented in hexadecimal. So 7 means, if you turn it into bits, this is just 4-bit value, meaning 0, 1, 1, 1, right? But if you add one more bit, 1 to the beginning, so if you replace 0 with 1, it turns into F. So F means 4 many ones, 1, 1, 1, 1. Okay, so actually, as you can see, we are making very small changes to this message X1. So you are just flipping a few bits, represented as red here, but the outputs are identical. So 2 different inputs, but same output. So this is what we call a collision in hash functions. So it is very easy to obtain this and many others in less than a second. Okay, you can produce hundreds of collisions for MD5 in less than a second. So this is why actually people should have stopped using it years ago. All right, let's move on to SHA2. This is developed by NSA and first published in 1993, but then they made a small modification. So because of that modification, we call it the initial version SHA0 and the modified version SHA1. So they added a single bitwise rotation. I think this one was added later. So this is why we have this one in SHA1. And this is made in 1995 and renamed as SHA1. So it looks like MD4 or MD5. The block size is again 512 bits. But now the output sizes change. It is 160 bits. So this is why instead of 4 words, we have 5 words here. Recall that these are 32-bit words. So 5 times 32 becomes 160. Number of runs also increased. Now we have 80 runs. So you perform this operation 80 many times. As you can see, it is a little bit more complicated, more additions and so on. So let me show you how this works in practice to visualize how a hash function works, okay? So assume that my input message is ABC. This is in actually ASCII, okay? So just create a TXT file in your computer and write ABC in it, okay? So this is 3-byte value. This is not hexadecimal, okay? This is just characters, ABC. So what you do is as follows. Now, you turn it into your first block, right? Because although you have 3 bytes, block size is 512 bits, right? So this is just 24 bits. So what you do is as follows. You turn this into hexadecimal. So in the ASCII table, recall that A is 61, B is 62, and C is 63. Now you perform the padding. Padding is just putting one bit as 1 and then fill it with zeros. This is why you see the value 8 in hexadecimal, okay? So you fill it with zeros until the end, but at the end, you write the length of your input message. In our scenario, this is 3 bytes, in other words, 24 bits, so you write 24 here, but as integer 24, when you turn it into hexadecimal, it turns as 18 here, okay? So this is how you start. So you have the input message, you turn it into a message block as 512 bits. Your IV is this. This is probably randomly chosen in the design phase. So this is written. This is what is written in the standardization documents. But generally, they are chosen in a very simple scenario. So we believe that IVs don't have any backdoors and so on. Okay. So you start performing these operations. Recall that I write the IV here, start feeding the message from here, S32 bits and so on. And, after the first round, you obtain this value. So after the second, you obtain this and so on and so forth. So you repeat this process 80 rounds. And at the end of each round, the output is as follows. It goes like this. And at the end, you obtain some values here. These values actually belong to these 5 words here, okay, at the end of the 80th round. So you take them here and write it here. Also, you write the IVs initially and add them. This is just regular addition, modulo 2 to the 32, and you obtain these values, and this is your hash, okay? So if you want to take the SHA1 hash of ABC as the message, this will be your output. These are important. I actually represented in all of the round values on the screen because this is how you test if your SHA1 implementation is correct, okay? You can use them as test vectors. You can print on the screen your round outputs to see where you're doing it wrong. And initially, if you are implementing a cryptographic algorithm for the first time, generally people make implementation errors, so it is generally hard to implement it correctly in the first time, okay? But this is how it works, okay? So let's go back to this part. We said that the message digest length is 160 bits for SHA1. So for pre-image resistance and second pre-image resistance, brute force attacks would require 2 to the 160 operations. But for collision, we need 2 to the 80 operations, right? But years after it is announced, Wang et al. Obtain a collision attack, which requires 2 to the 63 operations instead of 2 to the 80. So this is a lot faster than 2 to the 80. But at that time, we didn't have enough computational power to check if this attack works. But theoretically, we knew that it was broken. So, but recall that obtaining SHA0 collisions are really fast. This actually justifies the modification NSA made, okay? So if you just remove one bitwise rotation, you can easily break SHA1. So browsers of Microsoft, Google, and Mozilla stopped accepting SHA1 SSL certificates by 2017. Again, maybe just after 2017, you started to have some errors visiting some web pages, but of course, later on, they updated their certificates and move on to SHA2. And Bitcoin scripts allows SHA1 with the opcode op-SHA1, but it is not used in practice. When by practice, I mean it is not used in address derivation or transactions and so on, but since it is there, you can use it. And there is a very nice example called SHA1 bounty, which I will explain once we talk about Bitcoin in the future, okay? So let's talk about why SHA1 is not secure, because we can find collisions. So I told you that theoretically we could find years ago, but practically we couldn't because we didn't have the computational power. But Mark Stevens did the following. So he and his team had 64 GPUs, GTX 970, and they performed 2 to the 57 SHA1 evaluations and obtain the collision as follows. So this is the message 1, this is message 2. Both of them had the same output. But here there is a trick. Here, Mark Stevens did the following. Instead of using the same IV, they use different IVs. So for instance, as you can see here we have 90, here we have 91. So this is actually doesn't make much sense in practice, because in practice we use the same IV, a fixed IV, right? But here Mark Stevens is trying to show that we can find a real collision if we have enough computational power. So a free start collision breaks the inner layer of SHA1, does not directly translate into a collision on the full SHA1, because the attacker is not able to choose the initial internal state or the IV. But the thing is that Mark Stevens was trying to prove that if I had more GPUs, I could find a full collision for SHA1. And he was right, because he did this in 2015. And after that, Google said that they had a lot of GPUs. So they allowed Mark Stevens and team to remotely connect and use those GPUs to find a full SHA1 collision. And in 23rd of February 2017, Mark Stevens' team with Google actually obtained the SHA1 collision. And this is not one message block, but two message block collisions. You can see that IVs are identical now. You have two message blocks, the red and blue ones where you have the differences, but the output here and here are identical. So this was important, and actually this was used in SHA1 bounty, which I will explain when I finish talking about Bitcoin and show you how you can use this collision to solve the SHA1 bounty. All right, let's move on. So SHA1 is broken. But we still want to use an algorithm that has a short output, like 160 bits, like SHA1. In that scenario, you can use RIPEMD 160. This time, it is not developed by NSA. It is developed by academicians, cryptographers in 1996. It looks very similar to SHA1. And if you use the 160-bit output version, it is still secure, so there are no attacks. As you can see, it looks very similar to MD4, MD5 or SHA1, but the good thing is that there is no better attack than birthday paradox. So RIPEMD is secure. So RIPEMD 160 is the only remaining 160-bit digest size hash function that has not been broken yet. It was developed in the open academic community in contrast to the NSA designed SHA1 and SHA2. And Bitcoin script allows RIPEMD 160 with the opcode op RIPEMD 160. And actually, this is how you create Bitcoin addresses at the end. So Bitcoin uses RIPEMD after using SHA-256 for address generation with the opcode op hash 160. So if you use this opcode, it only performs RIPEMD hashing. If you use this one, it first uses SHA-256 for the input, and the output is then fed into RIPEMD 160. And we will talk about them when we talk about Bitcoin in the future. Okay, let's move on to the final Merkle-Damgard example we have. It is SHA2, and it is still secure, and this is what we use in practice most of the time. It is again developed by NSA, first published in 2001, but this time the message digest length is increased. Okay, as you can see, there are 4 variations. You can choose which one you want depending on the context. But when we say SHA-256, we talk about this value, this version. Okay, but you can also choose SHA-512 if you want. So the block size actually depends which message digest length you choose. So for the first one, if you choose 224 or 256 outputs, the number of runs is 64, and also block size is 512 bits. But for the other values, this also changes. So again, since the output is increased, we have more words, as you can see here. In order to provide confusion, now we have more operations because we have more words. As you can see, we have now functions like majority, sigma 0, sigma 1, and so on. But these are very similar to MD5. As you can see, they are defined here. For the sigma 0 and sigma 1, you take the input, rotate it 3 times for itself, and XOR it. and the other functions work like the ones we had for the MD4 or MD5. So it is very, very similar to previous designs, SHA1, MD5, and so on. But the good thing is that we don't have any attack. So pseudo-collision attack against up to 46 runs of SHA256, which is 64 runs, so it doesn't break the full SHA256. There are some premise resistance attacks from 2011 that breaks premise resistance for 57 out of 80 runs of SHA512 and 52 out of 64 runs for SHA256. SHA256 is extensively used in Bitcoin, so there's an opcode for that. But also, if you use the opcode #256, it applies SHA256 twice. Okay, so Bitcoin uses SHA256 a lot. So before conclusion, let's talk about password hashing competition. As I mentioned, hash functions also used for hashing passwords, and password hashing is everywhere. We're still using passwords everywhere. We cannot get rid of them, but there wasn't established standard to fulfill the needs of modern applications and to best protect against attackers. So as I mentioned, we can calculate SHA256 of a password thousands of times, but there isn't any rule or standard for that. So for this reason, there was a competition initialized by Jean-Philippe Omoson in fall 2012. The web page is here. You can find the detailed info there. It received 24 submissions. 9 finalists were announced in December 2014, and in July 2015, Argon 2 was announced as the winner. 4 other finalists are received special recognition, and their names are Catena, Lyra 2, Magva, and YesCrypt. You can see that Argon 2 or Lyra are used in some mining puzzles of alternative cryptocurrencies. This is why I'm mentioning them right now. But the idea behind these algorithms was to design it so that they are also memory intensive, so it is hard to produce an ASIC for them, a dedicated hardware for these devices, because for the Bitcoin mining, we have dedicated devices which can calculate SHA256 for very fast way. So in order to avoid this kind of brute force attacks, this was one of the aims of this competition. So these algorithms have some parameters to prevent, dedicated hardware design that are a lot faster than CPUs or GPUs.